There are some things that are difficult about polynomial functions, especially factoring and dividing. But graphing them isn't so bad, especially once they're in factored form. There really are just three rules you need to know. The first two have to do with end behavior, which is what happens on the far left and far right sides of the graphs, ignoring any wiggles in the middle. If we look at this graph in red, to describe its end behavior, we would say that it goes down on the right side and down on the left side. To look at another one, we would say that this goes up on the right side and down on the left side. That's it. That's end behavior. It either goes up or down. The first rule is about the right side of the graph and the end behavior on that side. The end behavior on the right side of the graph is solely determined by whether the coefficient of the highest degree term is positive or negative. These two graphs both have positive leading coefficients, and both of these graphs go up on the right. Whereas these two graphs both have negative leading coefficients, and they both go down on the right. If it's positive, it goes up on the right, and if it's negative, it goes down on the right. That's it for end behavior on the right side. The second rule is about the left side of the graph, and this has to do with the degree of the function. Remember that degree refers to the highest exponent present in the function. Let's start with two functions of even degree. Remember that even exponents give you the same result whether you input a positive or negative number. For example, 3 squared equals negative 3 squared, or 1 to the fourth equals negative 1 to the fourth. So it makes sense that even degree functions will have the same end behavior on both the positive and negative sides of the graph. If the right side goes up, so will the left, as you see in the green one. If the right side goes down, so will the left, as you see in the red one. Recall that odd exponents give you opposite results when you input a positive versus a negative number. For example, 2 cubed equals 8, but negative 2 cubed equals negative 8. So odd degree functions will have opposite behavior on the positive versus negative sides of the graph. If the graph goes up and to the right, as you see with the blue one, it'll go down to the left. If the graph goes down to the right, as you see with the purple one, it'll go up to the left. These two rules combined tell you about end behavior. And notice that nothing except the very first term is relevant when you're looking at end behavior. The third rule tells us about what happens at roots, which of course are the same things as zeros and x-intercepts. In this graph, for example, one of the factors is x plus 2. That means there's a 0 at x equals negative 2, and the graph goes through the x-axis at that point. There's another 0 or root at x equals positive 1. The graph goes through the x-axis at that point. And a third 0 at x equals 3, and the graph goes through the x-axis at that point. We also know that when there is what we used to call a double root, and we now call a root with a multiplicity of 2, the graph bounces off of the x-axis at that point. Here there's a 0 at x equals negative 2, but with a multiplicity of 2, and so the graph bounces off the x-axis at that point. And then at x equals positive 1, it goes through the x-axis. It may come up, so note that a root with an odd multiplicity greater than 1, as we see in this final graph, if it's odd, it seems to sort of hesitate before eventually going through the x-axis, as we see here at x equals negative 2. If it's an even multiplicity, it basically bounces off the axis and looks exactly the same as it would if it was a double root like we've seen before. Finally, note that you will not be asked to graph polynomial functions with complex roots other than the quadratic ones that we've done already.